Good afternoon, everyone. Today we're going to do two examples of looking at the characteristics of different polynomials. So our first one, we're going to have a degree 4 polynomial. We see that it's degree 4 necessarily because the highest exponent on any of the terms is a 4. And so we typically call that n. N is the degree of the polynomial, let's say. And so in this case, n is equal to 4, okay? We'll use that for convenience later on in our example. And so first off, we have a positive leading coefficient, right? Positive leading coefficient. And the leading coefficient is defined as the coefficient of the term with the highest exponent of the variable. For here, that's straightforward enough. That's our x to the 4 term. And so we have a positive 3 leading coefficient, which means we have a positive leading coefficient with an even degree polynomial, right? We have degree 4, which is an even degree, obviously. And so we know that if we sketch this very roughly on a graph with the y-axis and our x-axis, we know that since it's a positive leading coefficient, it's going to start high in the negative x direction. So we're going to start off here in quadrant 2, and then it could look a little differently in the middle, but it will probably look something like that. And then, since it's again an even degree polynomial, it's going to go back up and finish off like that. And since it's a polynomial, we know it's extending infinitely in both x directions, positive and negative. And so we're starting out. Again, starting means the negative x direction, so far to the left. We're starting out in quadrant 2, and we finish off, as x gets more and more positive, we're going to finish off our polynomial in quadrant 1. And so that answers our end behavior. We have quadrant 2 all the way through to quadrant 1. Now, the domain is simply what values of x can the polynomial take on. Are there any restrictions on values of x, potentially? I don't see any at all. This is a nice smooth polynomial. There's no breaks in the polynomial. There's no values that x cannot be. And so quite simply, x can be any element of the set of real numbers. Or as you might have heard, x belongs to the set of real numbers, x, er, whatever you want to read it as. Next we have the range. Range is the restrictions on the y values. Now the y values can go, as we can see, they can go as high as possible, but can't go any lower than what we call the minimum of the function, okay? Now, if this is a new term for you, don't worry, the minimum is quite simply what it sounds like. It's the lowest point on the function. So let's say, for argument's sake, that it is here for our rough sketch of a degree 4 quartic polynomial. Let's say that's our minimum. Again, oftentimes that's very hard to calculate. We'd have to use some graphing software, whether it be a website online like Desmos, Wolfram, or some graphing calculators. That they can do that really, really easily, and they can conveniently give you the coordinates of that minimum point. However, for our example, let's just make one up. Let's say this point is at -3 for argument's sake. So let's say this point is at, we say this point is at 2x and -3 in y. Then the range of our function, since we said that this was a minimum point for our function, that is the lowest point in the entire function, then this serves as the range of our function, in the sense that y has to take on values that are either on that point or greater, meaning higher up in the positive y direction. And so we can state our range as y being greater or equal to, because it can be exactly -3, or it can be greater, higher up. So y is greater or equal to -3, okay? And next, the number of possible roots. Well, it's a positive leading coefficient, which means it's going to be opening up. The y-intercept is -5, which means it has to cross the x-axis at least once to get down there, and then at least twice again to end up going back up. So it could have some double roots along the way, or it could, as we see in this example here, it could have up to 4 x-intercepts, 4 roots. And so for this specific example, we could say it would have 2 to 4, or we can say the number of possible roots. We could also just say up to 4. Okay? And again, the number of possible roots are always directly related to the degree of the polynomial, and that's just n shorthand, because we often describe n as the degree of our polynomial. Okay? So that is our first example for, again, a positively coefficient, even degree polynomial of degree 4. Okay? Again, very rough sketch. We'll fine-tune our sketches later on in the year. Example 2, this time we have a negative leading coefficient, and we have an odd degree polynomial, a cubic of degree n equals 3, right? Again, we're going to use the notation of n being the degree of our polynomial. Saves us a lot of writing. So now, if we go ahead and try to provide an answer for all 4 of these questions, we can write number 1, again, remind you number 1 is simply the domain. If we try to sketch this very roughly on a graph, let's do that first for convenience's sake. We can make a nice quick graph with an x and a y-axis. Now, a positive leading coefficient with a cubic function would go low to high and go quadrant 3 to quadrant 1. This is flipped over. This is reflected in some sense. And so since we have a negative leading coefficient with a cubic function, we know we're going to start high and end low. When I mean start high, I mean x in the negative direction is very, very high, and x in the increasingly positive direction goes infinitely low. Okay? So for part 4, which is the end behavior of our function, we can see that the end behavior is quadrant 2 all the way down to quadrant 4. So that's easy enough to start off with. The domain for polynomials is often fairly straightforward. There are no restrictions on the x values that this function can take, and so our domain is quite simply x ER, or x belongs to the set of real numbers, meaning x can take on any real value. Okay? The range this time is going to be a little bit easier to write because the y values aren't restricted in any sense. Whenever we have an odd degree polynomial, we see that it goes infinitely high to infinitely low, or vice versa, but in any case, the y values for the range are never restricted in any way. And so, making an analogy to how the x values aren't restricted, and so x can be any element of the set of real numbers, likewise, y can be any element in the set of real numbers, okay, y and r. And finish things off, third part of our solution here, the number of possible roots. So analogous to how the number of possible roots for an even degree polynomial was directly related to the degree, i.e. n, degree of 4, and we had up to 4 possible x-intercepts, 4 possible roots. We have the exact same idea here with the cubic function. It's not necessarily the case that there will always be exactly the same number of roots as the degree indicates, but that's a possibility. It could go. There's a possibility that it could go that high. And so, in this cubic function that I drew off of my head here, we do see 3 roots, 3 x-intercepts. And so, for the number of possible roots, we can simply say up to 3. There's always going to be at least 1 because, again, infinitely high to infinitely low has to eventually cross that x-axis boundary to go down into the negatives. So there's at least 1, and then depending on double roots or other roots, there can be 1, 2, or 3 in cases like this. So I hope this helps. I hope you're starting to see patterns between the even and odd degree polynomials, positive and negative leading coefficients. If you have any questions, comments, suggestions, please do leave a message down below, and have a great day.